Similar to this, can this have resonance? Yes, no, maybe. Can it do resonance?
Yes.
Yes. Where, what, why?
Oxygen has the lone pairs.
Exactly.
Yeah.
Allylic lone pairs that are on an atom next to a double bond. Agreed?
Yeah.
Now here's where I need you to do a little brainstorming or a little critical thinking and tell me. In this example, coming back, and put your pens down, let's understand, absorb. In this example, I drew the electrons going in that direction, right? Why? Could I not have shown them going in the other direction? Right, because it's carbon, 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 carbon. Who's pulling more? Who's pulling electron density more? Carbon or carbon or carbon or carbon?
Same.
Same.
Right? What about here? We have a choice. Either moving the electron density in this direction or moving the electron density in this direction. Who's going to pull more? Carbon or oxygen? Why? That's it. It's more electronegative. It's greedier. It wants electron density. So there it wouldn't have mattered, but here it matters. Which direction should I push the electrons in?
Left and
Towards
down.
oxygen. Because that's more electronegative. Is that making sense, everybody?
Yeah.
So let's draw the curved arrows. So those electrons move there. Where do the pi electrons here go? They go to the oxygen. So what's the outcome? What is that creating? Again, resonance structure uses this arrow. Skeleton does not change. The sigma skeleton does not change. But where are the pi bonds now?
Pi bond is the carbon cation.
What about lone pairs? Oxygen had 2 lone pairs earlier. How many does it have now?
3.
What about charges?
Negative charge on the oxygen.
Negative charge on the oxygen, so where something has to have positive also, because again, you were neutral, you should be neutral.
Carbon has the
Positive. Do you all agree? That's the resonance. Let's draw the hybrid. What would the hybrid of these two look like? What would be the combination, the middle, so to speak, between these two? Skeleton does not change. In fact, that's what I do, is I first draw out my skeleton because I know that won't change. And then the delocalization. Which atoms are participating in this delocalization?
The carbon and the oxygen.
Which carbon and which, there's only one oxygen, but which carbon?
Carbon on the far right.
All of them,
All the
right?
carbons.
The electron density is flowing between this carbon, this carbon, this carbon, and oxygen. It's this entire piece that is being used to move electron density. Isn't that right? So when you're drawing the hybrid, basically I'm going to draw a dotted line using all of those atoms, because that's where the delocalization is. Now the charges, where are the charges? What are the charges?
Partial plus on the end carbon and
And?
a partial minus on the oxygen.
Yes,
How would lone pairs look like
what do you mean?
if we were to draw lone pairs in oxygen? Because we're going
In the hybrid model.
So once again, I'm not a good drawer, so I'll try my best. The sigma skeleton does not change. Now every atom is sp2 hybridized, right? That's sp2 hybridized has an unhybridized p orbital with 1 electron in there. The other one is also with 1 electron, opposite spins. Fine. This is also sp2 hybridized, has electron in it, and then oxygen is also sp2 hybridized, so it has a p orbital. Now how many, and then when all of them merge, how many total electrons are being delocalized? Anybody? What's the total number of electrons participating in this resonance? Careful, let's count. How many electrons there? That's a double-headed curved arrow,
Yeah, there are two
electrons.
electrons there and then
right?
So it's 4.
And how many electrons here?
4.
So what's the total number of electrons participating in resonance? All 4 of them are in this entire space at all times. Electrons, I know you guys have studied in Gen Chem, electrons have particle nature and wave nature. Waves are not here or there, waves are everywhere. So electrons, those 4 electrons are not here or here or here or here, they're everywhere. They're filling up that entire space. So one of those 3 lone pairs is delocalized.
Mm-hmm.
What about the other 2 lone pairs that are not part of resonance? This is sp2 hybridized, right?
Yep.
So there is an sp2, lone pair, that's where those 2 exist. Only one of the lone pairs is delocalized, the other 2 are not. Is that what you were asking?
Yeah.
Yeah.
Yes?
But do you want us to draw it like in that way or
No.
that way?
That's just me trying to explain 3-dimensionally speaking, and I don't know how good a job I'm doing with my drawings. No. We draw hybrids like this. Are we okay? Yes?
Go back just a second.
Yes.
So there are 6 total participating.
In this example, 4. Oops, that's 3. 4. 2 electrons coming from here, 2 electrons coming from there, that's it.
And then the
Those 2 are not participating.
Oh, I see, okay.
Yeah, those are in the hybrid orbitals. Only one, so there are 3 here, but only one is part of resonance, the other 2.
Thank you.
Yeah.